point estimates before, came up in the past few sections. We know our point estimate is that one example of it has been p-hat. A point estimate in general is just something that we gather information from the sample and use it to make some kind of inference about the population. So a point estimate is just a statistic. So from the sample, we're using to estimate the parameter or the population. We've been talking about the point estimate for p-hat, but the next step is the point estimate for x-bar, for the sample mean. So first example. Pennies minted after 1982 are made from 97.5% zinc and 2.5% copper. The following data represents the weights of 17 randomly selected pennies minted after 1982. To create the data as a simple random sample, estimate the population mean weight of pennies after 1982. So, do I have the data from every single penny made after 1982? No. We are estimating the population mean by finding the mean of this group. How would you find the mean of it? Right. So, mean, you add them all up. I am not taking the time to write all those down. And we will divide by 17 because that's how many points we have. So, grab your calculator. So, the sample had a mean or an average of 2.464. So, the best guess I could give is the whole population. That would be the weight. Okay? But, if I went out and collected 17 different pennies, do you think I would get the same average weight back again? No. So, this is the whole p-hat example we had last time where we said if we went out and collected all these different samples, we would get a different answer every time. So if I'm trying to estimate the population, instead of just giving a single value, I really need a range of values. So that's where the confidence interval idea comes in. Now, this one is different. We are going to be using the t distribution. Everything we've done for a long time has been all about the normal table. We are now going to talk about the t distribution. So, this is our formula. If you look at your formula sheet for chapter 9, this is I don't think they have this one exactly on there. We're going to talk about some other variations of it. So, it's on, well, a similar version. Okay, that's all right. So, this is what's called a t distribution. N minus 1 degrees of freedom. N is the number in your sample. So, on my pennies, I had 17, so we would call it 16 degrees of freedom. X bar represents the sample mean. S represents our sample standard deviation. In this, you would have to have a mu, so a population mean, in order for that to work. So this next example isn't really anything for us to calculate. I've generated some data and made some graphs to illustrate something. If I obtained 1,000 simple random samples of size 5 from a normal population that has a mean of 50 and standard deviation of 10, and I want to determine the sample mean and sample standard deviation for each of the samples. One of them, Z, the idea with Z, it's based off sigma, the standard deviation of the whole population. T is based off S, the standard deviation of the sample. Okay, so the only difference between these is Z uses the population standard deviation, T uses the sample standard deviation. And when we look at the graphs from this, if you look at the next page, if you had found these 1,000 samples and looked at it, if we look at the Z, it's pretty well bell-shaped, isn't it? So it's pretty symmetric, bell-shaped, kind of looks like a normal distribution. How is T different? It's still generally bell-shaped.
It doesn't have as many bars.
Okay, it's more spread out, isn't it? We've got a lot more bars on the end, not as much in the center. So what we see is Z is our standard normal. Pretty much everything was between -3 and 3, centered at 0. But when you look at t, it went from -10 all the way to 10. And so when I look at t, it's still symmetric and bell-shaped, but it's more spread out. So it doesn't really follow the true normal distribution. The reason it's so spread out is because it's based on the standard deviation of the sample versus the whole population. And in general, the sample is going to have more variability than the entire population. And so because the sample would have a larger standard deviation, the distribution is more spread out. Okay, so some properties of it. Again, this isn't really what I'm testing you over. All of this is just kind of some background on what this t distribution is. The things that I'll be asking you to do is really just the confidence interval stuff later on. The t distribution is a little different because we have degrees of freedom here. It is still centered at 0 and symmetric. The area under the curve is still 1, half on each side, just like with the normal. It's never going to be 0, just like the normal. But the difference here is the area in the tails is greater than the area in the tails of the normal. Okay, it's a little more spread out because we are estimating the population standard deviation, so there's more variability here. That's really the big difference. The idea, if your sample gets bigger, the larger the sample, the better your data is. And so if we were to compare like the t distribution with 5 versus 15, as your sample gets bigger, it's going to look more and more normal. Just like with most things we've seen, if our sample was big enough, it would be normal, and that's kind of the same thing here. Okay, so that piece of paper, that's your background knowledge. Next sheet of paper, this is what I will be expecting you to do. We still have with the normal, we had the Z alpha notation, same thing now with the T's. When I talk about the T alpha, alpha is the area to the right. Okay, so just remember that. Table always gives you area to the left for the normal. When you're looking, we actually have a table for our T values, but this one is different. If you flip in your formula chart, in your formula sheet to the T distribution, if you look at the picture up at the top, this table actually gives you the area to the right. So
we could have used this one the whole time.
No, because it's going to have different numbers. But whereas the normal table told you area to the left, this actually has the area to the right. So it is a little bit different. Okay. So, fine. So we're going to use our tables now. The T value, such that the area under the T distribution to the right is 0.2, assuming 10 degrees of freedom. Or you might see me write it as T sub 0.2, 10 degrees of freedom. So if you look, on the left-hand side of the table, it has your degrees of freedom. So we're going down to the 10. And then at the top, it has your probability, your 0.2. So I'm going over to the 0.2, and we get
2.359. Oh, 0.2.
0.879. So that would be the T value that would give me an area of 20% to the right. If I asked you to find, no, I'll do that. Let's do. Why don't you guys take a second and see if you can find that one. Okay, so this one we have our 0.1 with 15 degrees of freedom, and you get. Okay, so what that means is the area here if this is 0.1, then our t-value would have to be 1.341. Now, what if I said, find the t-value. So the area to the left is 0.0025 with 27 degrees of freedom.
So we just look for the point. No.
Okay. Your normal table gave you both sides, the positive and the negative. The t-distribution is smaller. It's expecting you to know a little bit about symmetry. Keep in mind, both of these are centered at 0, right? These are negative t's over here. These would be the positive t's over here. Your table only gives you the positive t's. But we want the area to the left
So it's the same.
to be 0.0025. So let's find the one where the area to the right would be 0.0025, because that's what our table tells us. So we need to go 0.0025, 27 degrees of freedom, and that is, what'd you say?
3.057.
Okay. But this is symmetric. So if this value is 3.057, I really need this one over here. What would it be?
Negative.
Negative. Because these tails are equal, if I asked for the area to the left, you're just reading it from the table, and you would do the negative to get the other side.
Why is this one negative and the other one's one minus? We want the other side. Because
You're talking about different things. If I wanted the area in here, that's 1 minus. I'm just talking about the t-value itself.
Okay.
So it's a negative t-value. Okay. Any questions there? So let's talk about the confidence intervals. When you're calculating the confidence interval for p hat, like we did yesterday, if you remember your formula, it was all based on the z values, right? You had to have your z alpha over 2 and your p hat, and then you could make your confidence interval. If we are talking about a confidence interval for the mean, then we are going to be using our t-distribution. A few requirements. The data has to come from a random sample, has to be less than 5% of the population, and then either the original data was normal or our sample is large for this to work. To make the interval itself, this is the piece that is on your formula sheet. If you are talking about x bar, it's going to be x bar plus or minus t alpha over 2 times s over radical n. So it's very similar to the one we were doing before, but slightly different. Okay, we are using the t-distribution, we are using the sample standard deviation here. No, it's on chapter 9, it's right under the second bullet under the confidence intervals. Okay, we are going to make a confidence interval. You guys need a calculator here. I am giving you raw data this time. I did not just say, here's all the stuff, figure it out. I actually just gave you the original data. So the data shows the reported miles per gallon of the 2011 Ford Focus automobiles for 16 different owners. Treat the sample as a simple random sample of all 2011 Ford Focus. So would 16 be less than 5% of the population?
Yes.
Yes. Okay, create a 95% confidence interval. To make the confidence interval, if you are looking at the formula you wrote down, we need x bar plus or minus the t alpha over 2 times our s over radical n. Okay, I need my x bar and my s. Since I have given you the original data, we're going to do something we haven't done in a while. You are going to go to Stat, Edit, and you are going to put all this in your L1. So clear out any data that's in there, enter this stuff into L1. Then remember the next step was to go to Stat, go over to Calculate, and we want number 1 variable statistics. If you enter through that screen, it should tell you your X bar and your S. So I got an X bar of 36.8 and an S of 2.917. Yes, ma'am. Do you go to Stat, Calculate, 1 variable statistics. For lists, it should say L1. Frequency list, it should not say anything. So if it says L2 there, delete that. And then you should be able to calculate. Did that fix it? Okay. Now I need my T alpha over 2. So we have to think. If I want 95%, that means the tail is 5%, right? So that's like 0.05 over 2 or T 0.025. Now I need my degrees of freedom. Degrees of freedom is always 1 less than the number in your sample. So how many were in my sample? So my degrees of freedom would be 15. So you're going to your table. Your degrees of freedom is 15. My value at the top is 0.025. And I get 2.131. So now we are ready to make our confidence interval. Oh, I did not mean to scroll down quite that much. So now we do X bar. So 36.8 plus or minus the 2.131 times S, 2.917, over the square root of n, and n was 16 here. And I get interval from 35.246 to 38.35. You will get slightly different numbers depending on what you round your standard deviation to. So this is where work is really important. I need to know what you're using for your S. I need to see exactly how you're getting your calculations. Okay, the interpretation for this is just like when we interpret p hat. So it means we are 95% confident the mean, so the true mean, is between 35.246 and 38.354. So this is extremely similar to what we were doing, except you are using the table for T instead of Z. I'm not always going to give you just a list of numbers. Sometimes I will just tell you in the problem X bar is this and S is this, and all you have to do is plug in. So it can go either way. Any questions on that? Okay. Let's do a couple more. We're going to only do probably one more confidence interval because it's pretty much the same thing. I want a 99% confidence interval about the mean of pennies weighted after 1982. So what I want you to do is use your calculator to find your X bar and your S on this. So we got X bar to be 2.464 approximately. Standard deviation, I guess I took my mean to 3 decimal places. I'll go to 3 here. I'll be consistent. So 0.018 approximately.
So do you have to only do 3 decimal places?
You can do 4. There's really no rules on this. Okay. So now we need our t value. So my alpha would be 0.01 divided by 2, so this is t.005. How many degrees of freedom do we have here? 16. There are 17 points, so that means 16 degrees of freedom. So I need the 0.005 and 16, and I get 2.921. So then create your confidence interval. X bar, 2.464, plus or minus your t, 2.921, times your s, 0.018, over the square root of n. So I get an interval 0.2451 to 2.44 or 477. Again, if you rounded your S differently, then you might get a slightly different interval. Slightly different, I mean like the nearest thousandth might be off, last decimal place might be.
You did 2.46, not 2.464. Is that what I thought was it?
Yeah. Yes, ma'am.
I'm sure it's so bad right now. Because like you can spend shuffling and like I you're so bad. Your L1. I need to get it trimmed because I already have that brush it. It's always like bad in it. This much.
It'll be good for that one. All right. Other questions? Okay. Other questions here?
Even if you did.
Okay, the last thing, similar to yesterday, we talked about if I needed to decide how big my sample should be. There is a formula for that. So this is on your formula sheet. In the chapter 9 part, you've got Under the confidence intervals, the first one is what we use for p-hat, second one is what we're using for x-bar. On the sample size, the first bullet is the p-hat stuff, the second bullet is this x-bar. We do go back to z values when we're talking about this x-bar, or when we're talking about the
other one now?
only if I'm trying to find out how big my sample should be. Okay, so if I'm going back to that mileage problem we were looking at, and I want to know how large of a sample is required to estimate the mean miles per gallon within 0.5 miles per gallon, so that is my error, with 95% confidence. Okay, so we know, let's see, we need our z alpha over 2 if we're going to use this formula. So I'm trying to use my n equals z alpha over 2 times s over e squared. So we're going to use that formula. So we need to find all these variables. I know my e, z alpha over 2, 95%, so that's 0.05 over 2, z 0.025. That means in the table, it's 97.5 for the area, so we're back to our normal table. So the 0.975 is 1.96. Something I want to mention, I haven't showed you this before because I don't always ask for one of these percents, so you need to be able to know how to read the stream table. But look on the normal table, the bottom left. It tells you confidence interval for critical values is z alpha over 2. If you're at 90, 95, 98, or 99, it actually tells you what the z is. You don't have to read. Yeah. So if I give you one of those percents, like this was 95%, and I look, and it's 1.96, it actually tells you down there at the bottom. You need to know the other way in case I give you like 96%, but you could use this for the confidence.
This is when we just find like the 0.25.
The 0.975. Okay. Then the other piece of this I need is my S, which we did on the previous example when we entered all this in. 2.917. Okay. So now we can plug it in.
How do you find that if we didn't have?
I would either have to tell it to you or give you the data so you can plug it in your calculator and get it. From the previous example when we were doing the cars. Okay, and what'd you get? So that means we would need 131 people. Still round up. Okay, so this is the end of the section. Homework, we don't have a ton of time, but we've had a lot of work days lately, so I think this is manageable. There's 8 problems. They are not all